40 light years from where you're sitting right now, there is a planet that looks, on paper, like almost everything we've ever hoped to find. It's rocky. It's roughly the size of our own world. It sits at a distance from its star, where liquid water could, in theory, pool on its surface. For years, the entire scientific community quietly agreed on one thing: if we were ever going to find a world with a real shot at hosting life beyond Earth, this was probably it. So humanity did the only thing it could do. It built the most powerful space telescope ever constructed, spent $10 billion in 3 decades getting it into space, and pointed it directly at this planet. That telescope is James Webb, and answering the question of whether we're alone in the universe is quite literally part of its job description. After years of staring, after mountains of data so dense and so noisy that entire teams of scientists had to invent brand new mathematical tools just to make sense of it, the answer that came back wasn't yes. It wasn't no either. It was something stranger and honestly more unsettling than either of those. The scientists simply could not tell, not because the telescope broke, not because the planet is too far away to see, but because the star this planet orbits is doing something so chaotic, so relentlessly loud, that it's drowning out the very signal we built Webb to detect. Stick with me here, because what's unfolding around this one small, dim star might be one of the strangest and most important sagas in the history of the search for life beyond our solar system. The planet in question is called TRAPPIST-1e. But before we get into what Webb has or hasn't found, it's worth understanding exactly why this particular world made astronomers around the planet stop everything the moment it was discovered. 40 light years sounds like an unimaginable distance, and in a very real sense it is, but in cosmic terms it's practically next door. Our galaxy alone stretches about 100,000 light years from one edge to the other, so a system sitting just 40 light years away is, relatively speaking, in our backyard. And in that backyard sits a small, dim, reddish star called TRAPPIST-1. It's tiny, roughly the physical size of Jupiter, but unlike Jupiter, it's made of true stellar material, dense and burning with nuclear fusion at its core. Orbiting tightly around this modest little star are 7 planets. 7 roughly Earth-sized rocky worlds, all packed into orbits so close that the fastest of them completes a full year in about a day and a half, and even the slowest, outermost planet finishes its orbit in less than 3 weeks. Every single one of these 7 worlds circles its star closer than Mercury circles our Sun. In fact, if you took the entire TRAPPIST-1 system, star and all 7 planets, and dropped it into our solar system, the whole thing would fit comfortably inside the orbit of Mercury, with room left over. Now, your first instinct might be to assume that planets crammed in that close to their star must be scorched, uninhabitable furnaces. But here's the twist that makes this system so remarkable. TRAPPIST-1 isn't anything like our Sun. It's small, cool, and dim, so dim that to feel the same warmth on one of its planets that we feel here on Earth, you'd essentially need to stand about as far from it as Mercury sits from our Sun. Because the star is so faint, its habitable zone, the narrow band of distance where temperatures could allow liquid water to exist, sits extremely close in. And remarkably, 3 of the 7 planets fall right inside that zone: TRAPPIST-1e, TRAPPIST-1f, and TRAPPIST-1g. 3 potentially habitable worlds, orbiting the same star, packed closely enough together that a sufficiently powerful telescope could actually study their atmospheres in detail, and do it repeatedly. No other star system we know of offers anything like this combination. That's exactly why, when this system was fully revealed to the public in 2017, it made headlines everywhere, and why researchers began calling it one of the most important planetary systems ever found. It's also exactly why, when James Webb finally launched on Christmas Day in 2021, TRAPPIST-1 was near the very top of its target list. But to really appreciate what's happening now, it helps to rewind to how this system was found in the first place, because that story is almost as remarkable as the planets themselves. A Belgian astronomer named Michael Gillen was running a modest survey out of the Atacama Desert in Chile, not with some enormous, cutting-edge observatory, but with a comparatively small, 60-centimeter robotic telescope. He'd given it an affectionate name, TRAPPIST, as a nod to the Trappist beers brewed by monastic orders back home in Belgium. His project involved monitoring about 50 nearby ultra-cool dwarf stars, watching patiently for the tiny dips in brightness that would suggest a planet was passing in front of one of them. Somewhere around the 30th star on his list, something caught his telescope's attention. A dip, then another, then a cluster of dips arriving too frequently and too regularly to belong to just one object. Multiple bodies were clearly transiting this star. Gillen brought in reinforcements, ground-based observatories scattered across several continents, all trained on this same faint red star. By May of 2016, his team had enough data to publish their first results. 3 Earth-sized planets orbiting an ultra-cool dwarf star just under 40 light-years from us. It was exciting news, but not yet the discovery that would make history. That came next. NASA's Spitzer Space Telescope took over and stared uninterrupted at TRAPPIST-1 for 21 straight days, 21 days of continuous watching without so much as blinking. Buried inside that long, unbroken stream of data were 4 additional planets that ground-based instruments had completely missed. By February 2017, Gillen's team had the full picture ready to share with the world. 7 rocky, roughly Earth-sized planets circling one small red star, with 3 of them sitting inside the habitable zone. What makes this system even more extraordinary is the mathematical relationship between the planets' orbits. All 7 worlds are locked into what astronomers call a resonant chain, a precise interlocking rhythm where the orbital period of each planet falls into a clean numerical ratio with its neighbors. For every 8 orbits the innermost planet completes, the next one out completes almost exactly 5, and so on, all the way through the system. It's the longest unbroken chain of orbital resonance ever discovered around a single star. Billions of years ago, as these planets formed and migrated inward through the disk of gas and dust surrounding their young star, they essentially locked into place one after another like beads threading onto a wire, and that delicate arrangement has held steady for an estimated 6 billion years, making the system roughly 3 billion years older than our own solar system. This resonance isn't just a beautiful cosmic coincidence, it's also what allowed scientists to figure out exactly how massive each planet is, without ever directly imaging any of them. As the planets pass close to one another in their orbits, they tug on each other gravitationally, causing tiny shifts, seconds, sometimes minutes, in the precise timing of each transit compared to what simple orbital mechanics alone would predict. By measuring those minuscule timing variations with extraordinary precision, astronomers were able to calculate the mass of each world. And those masses told them something crucial. These are genuinely rocky planets with real solid surfaces, not gas-shrouded mini-Neptunes, not waterlogged worlds with no floor to stand on. Actual rock, the kind of surface you could, in principle, stand on. TRAPPIST-1, in particular, sits almost perfectly in the middle of the habitable zone, receiving roughly 2/3 of the energy that Earth receives from our own sun. Right size, right temperature range, right composition. On paper, it's the closest thing to an Earth twin that astronomers have ever identified, and it was built quite deliberately to be one of Webb's primary targets. Here's the plan scientists had in mind when Webb finally launched. As TRAPPIST-1e passes in front of its star from our point of view, a sliver of starlight filters through the thin envelope of gas surrounding the planet, assuming it has one at all. Different gases absorb light at very specific wavelengths. Water leaves one kind of fingerprint, carbon dioxide another, methane another still, and so on for oxygen and sulfur dioxide. By carefully analyzing exactly which wavelengths of starlight go missing during a transit, scientists can, in theory, reconstruct what gases exist in that atmosphere from 40 light years away, without ever sending a probe anywhere near the planet. It's one of the most elegant techniques in modern astronomy, and it genuinely works. It's been used successfully on large, puffy gas giants, whose thick atmospheres leave big, unmistakable signals. The real question was always whether the same trick could work on a small, rocky world, where any atmospheric signal would be roughly 100 times fainter. For TRAPPIST-1e specifically, the honest answer that's come back so far is not yet. And the reason why turns out to be something almost nobody fully saw coming. The problem isn't the planet, it's the star. TRAPPIST-1 is magnetically restless in a way that our own sun simply isn't. Its surface is constantly shifting. Dark star spots and bright hot patches rotate in and out of view as the star spins on its axis. Our sun has sunspots too, of course, but the sun is so large and so bright overall that a handful of dark patches barely register against the background when you're trying to measure the faint dimming caused by a transiting planet. TRAPPIST-1 is a different story entirely. Because it's so small and so dim to begin with, its star spots and bright patches can cover a genuinely significant fraction of its visible surface, and that surface keeps changing, sometimes noticeably within the span of a single transit observation. The star can look meaningfully different by the end of a measurement than it did at the start. This matters enormously because of how these transit measurements actually work. Scientists compare the star's brightness while the planet is crossing in front of it to the star's brightness when nothing is in the way. Any change in the star's own surface during that window creates a false signal, one that can look deceptively similar to genuine atmospheric absorption. Astronomers call this stellar contamination, and on TRAPPIST-1, the contamination shows up at amplitudes of hundreds to thousands of parts per million. Compare that to the atmospheric signal scientists are actually hunting for from a thin, rocky planet's atmosphere, at most around 100 parts per million. In other words, the noise coming from the star is roughly 10 times louder than the signal they're trying to detect. Imagine straining to hear someone whisper your name from across a packed stadium while a rock concert is blasting at full volume, and you've got a pretty good sense of the problem. It gets worse too, because this isn't random static that you can simply average away. Stellar contamination tends to mimic the exact shape and wavelength pattern of the very signal astronomers are searching for, which means you can't just filter it out the way you'd clean up noise from a staticky radio broadcast. The interference and the message look too much alike. Then, during one of Webb's actual observation windows for TRAPPIST-1e, things got worse in a very literal way. A powerful stellar flare erupted right in the middle of a transit, an enormous burst of energy from the star's surface that flooded the data with a signal completely unrelated to anything a planetary atmosphere could produce. That entire transit observation was effectively lost, too corrupted by the flare to be useful. In response, the research team spent well over a year building entirely new mathematical frameworks specifically designed to try to separate the star's chaotic noise from whatever faint signal the planet itself might be contributing. New models, new statistical approaches, techniques nobody had really needed before. And after all of that painstaking effort, the honest, unvarnished conclusion was this. They still couldn't say with real confidence whether TRAPPIST-1e has an atmosphere at all. While the team wrestled with that particular puzzle, Webb was quietly gathering cleaner, and in some ways more heartbreaking, data on the other planets in the system. TRAPPIST-1b, the innermost of the 7, was examined first. Using Webb's MIRI instrument, scientists measured the planet's thermal glow at a wavelength where carbon dioxide absorbs light especially strongly. If TRAPPIST-1b had a thick, Venus-like carbon dioxide atmosphere, that thermal glow should have come back noticeably dimmed, muffled by the blanket of gas overhead. Instead, the measurement came back bright and essentially unobstructed. A thick atmosphere was ruled out with better than 6 sigma confidence, a statistical certainty so strong that scientists would expect to be wrong about it roughly once in 500 million tries. TRAPPIST-1b, the closest planet to the star, is a bare, airless rock. TRAPPIST-1c, the next planet out, received similar scrutiny, and the results again pointed strongly away from any thick atmosphere, though with somewhat less certainty than for planet B. Then, in April of 2026, a paper published in Nature Astronomy delivered full thermal phase curve measurements for both B and C together, a far more detailed kind of measurement that tracks how a planet's brightness changes as it rotates and shows different faces to the telescope over time. The results were unambiguous. Both worlds radiate heat in patterns consistent only with bare rocky surfaces. Even atmospheres with pressures close to Earth's own sea level pressure were strongly excluded. That's 2 planets confirmed dead in a row. Next came TRAPPIST-1d, sitting right at the inner edge of the habitable zone and slightly smaller than Earth, arguably the inner planet with the best remaining chance of having held onto some kind of atmosphere. Results published in 2025 delivered a full transmission spectrum spanning a wide range of wavelengths. After scientists painstakingly corrected for the enormous stellar contamination polluting the raw data, contamination running into the hundreds or even 1,000 parts per million from the star's surface alone, what remained underneath it all was essentially a flat, featureless line. No methane, no water, no carbon dioxide, no carbon monoxide, no sulfur dioxide, nothing. The researcher who led that study summed it up about as plainly and painfully as possible. TRAPPIST-1d can be crossed off the list of potential Earth twins. That makes 3 of the 7 planets confirmed as bare rocks, 3 of the inner worlds belonging to the most talked about planetary system in modern astronomy, stripped of whatever atmosphere they might once have had, almost certainly by relentless radiation from their own star. And that leaves the entire weight of this search resting on a single world, TRAPPIST-1e, the one sitting comfortably in the habitable zone, the one where the orbital math and the energy budget both line up, the one where liquid water really could exist on the surface, but only crucially if there's actually an atmosphere there to make that possible. For a brief moment in late 2025, it genuinely looked like Webb might have found something. When researchers ran their carefully contamination-corrected transmission spectrum of TRAPPIST-1e through a whole battery of atmospheric models, something interesting popped out. Models that included methane in the planet's atmosphere consistently fit the data a little better than models that left methane out. It wasn't a clean, unambiguous detection, nothing close to a smoking gun, but it was a real statistical preference, a hint worth taking seriously. The data seemed to lean, ever so slightly, toward a scenario where TRAPPIST-1e carries traces of methane mixed into a nitrogen-rich atmosphere. The team floated a cautious comparison. TRAPPIST-1e might resemble a warmer version of Titan, Saturn's moon, which is famously wrapped in a thick nitrogen-methane atmosphere of its own. They started calling the hypothesis a warm exotitan. For a little while, it genuinely felt like the years of frustration might be paying off, like the data was finally, quietly, pointing towards something real. Then a planetary scientist named Sukrit Ranjan from the University of Arizona, who had been involved in all of the team's previous published work on the system, looked at the result from a different angle and spotted a problem that's almost poetic in how cruel it is. TRAPPIST-1 is cool enough, as stars go, that methane can actually exist in the star's own outer atmosphere. Not on any planet, but in the star itself. The outer layers of an ultra-cool red dwarf like this one are so much cooler than the surface of a sun-like star that relatively complex molecules, methane among them, can survive there without being torn apart. And methane sitting in a star's atmosphere leaves a spectral fingerprint that looks almost identical to methane sitting in a planet's atmosphere 40 light-years away. So when Webb picked up something that resembled a methane signature, there was suddenly no clean way to answer the obvious question. Is this coming from the thin ring of gas potentially surrounding the planet, or is it just more stellar contamination, mixed in with everything else the team was already struggling to strip away? Ranjan didn't soften his conclusion much. Based on the most recent analysis, he said, the tentative hint of a methane atmosphere is more likely to be noise leaking from the host star than a genuine planetary detection. But he was also careful to point out what that conclusion does and doesn't mean. It doesn't mean TRAPPIST-1e definitely has no atmosphere. It simply means the current data isn't good enough to tell the difference between a real planetary signal and an artifact of the star's own chaotic behavior. Two very different stories remain equally possible. In one version, TRAPPIST-1e is just another bare, irradiated rock, stripped of its air long ago like its inner siblings. In the other, it carries a thin atmosphere, probably mostly nitrogen, maybe with faint traces of other gases, that Webb's current observations simply aren't sensitive enough to pull out cleanly from underneath the stellar noise. What scientists can say with real confidence is what TRAPPIST-1e is not. It's definitely not shrouded in a thick, hydrogen-dominated envelope, the kind of puffy atmosphere you'd see on a mini Neptune. Webb's sensitivity was more than enough to rule that scenario out entirely. Whatever this planet turns out to be, it's evolved past that stage. It's something closer in character to Earth or Venus than to a gas-rich world, but whether it ends up looking more like a living Earth or a dead Venus, whether it has any breathable air at all, remains locked away behind a wall of stellar noise that nobody has yet found a way to fully tear down. Here's where the story turns from frustrating to genuinely inspiring, because science has a way of doing something remarkable even when the data refuses to cooperate. If the star itself is the problem, and at this point every single observation confirms that it absolutely is, then any real solution has to involve dealing with the star directly. And the research team eventually landed on an approach that sounds almost too clever to work. They decided to use a dead planet to help them find a living one. TRAPPIST-1b, remember, is the innermost planet, already confirmed beyond reasonable doubt to be a bare, airless rock. It transits the very same star as TRAPPIST-1e. And because TRAPPIST-1b has no atmosphere whatsoever to speak of, absolutely every spectral feature that shows up in its transit data has to be coming from somewhere else. The star. Every star spot, every bright patch, every faint molecular fingerprint bleeding out of the star's own outer atmosphere. All of it is pure stellar contamination with nothing from a planetary atmosphere mixed in, simply because there isn't one. That makes TRAPPIST-1b an almost perfect calibration tool, a kind of built-in noise filter supplied by nature itself. The technique researchers built around this idea is called the dual transit method, and the logic behind it is fairly elegant. When TRAPPIST-1b and TRAPPIST-1e happen to transit close together in time, astronomers observe both. They record exactly what stellar contamination looks like, stamped onto TRAPPIST-1b's spectrum during its transit. Then they subtract that same contamination pattern from TRAPPIST-1e's spectrum, recorded around the same time. Whatever signal is left over after that subtraction, whatever can't be explained purely by the star's behavior, either belongs to TRAPPIST-1e's atmosphere or it confirms there isn't one there to find. Either outcome would count as a landmark result. Early tests of this method back in 2024 and 2025 showed real promise. In cleaner observation windows, it measurably reduced the amount of stellar contamination bleeding into the data, exactly as the underlying theory predicted. But there's a catch, and it's a significant one. The whole method assumes the star's surface doesn't change too dramatically between one planet's transit and the other. The trouble is that on TRAPPIST-1, stellar flares erupt disturbingly often. And when one goes off between the two observations, the star essentially rewrites its own face within minutes. Suddenly, the contamination pattern recorded during TRAPPIST-1b's transit no longer matches what TRAPPIST-1e's transit is actually experiencing, and the whole calibration trick breaks down right when it's needed most. Despite that limitation, the team is pressing forward. They've laid out a program calling for roughly 15 paired dual transit observations, spread across multiple observing cycles on James Webb. The hope is that with enough individual data points collected over time, the statistics will eventually overwhelm the noise contributed by any single flare event. Ryan McDonald, one of the researchers driving this effort, has estimated that the next major update on TRAPPIST-1e's atmosphere, one way or the other, should arrive sometime around early to mid-2027, and Webb won't be working alone on this problem for much longer. NASA's Pandora mission, a small, dedicated satellite, is being built specifically to monitor host stars in both near-infrared and visible wavelengths before, during, and after planetary transits, with the explicit goal of mapping out stellar noise so it can be subtracted from planetary observations with far greater precision. Meanwhile, 3 extremely large ground-based telescopes currently under construction are expected to attack the same problem from a completely different angle, using extremely fine spectral resolution to separate planetary signals from stellar ones, based on the slightly different Doppler shifts each produces as the planet moves through its orbit. And further out on the horizon, NASA's Habitable Worlds Observatory, currently projected for some time in the 2040s, is being designed from the ground up to directly image potentially habitable planets by suppressing the blinding light of their host stars by a factor of roughly 10 billion. That's not inferring a planet's properties indirectly from filtered starlight. That's isolating the planet's own light directly, which changes the entire nature of the search. In January 2026, NASA already awarded technology development contracts to 7 different companies to begin building the engineering that mission will eventually require. So where does all of this actually leave us? 40 light years away, on a planet that may or may not have an atmosphere, sitting in a habitable zone around a star that simply refuses to stop shouting over the very signal scientists are trying to hear, the honest answer is, we still don't know. 3 of the system's 7 planets are confirmed dead rocks. That much is no longer in question. And that fact alone carries a sobering implication. Red dwarf stars like TRAPPIST-1 are the single most common type of star in the entire galaxy. And if they're violent enough in their youth to strip the atmospheres off their closest planets entirely, then perhaps the habitable zone worlds that managed to survive that early bombardment are the rare exception rather than the rule. If TRAPPIST-1e ultimately turns out to be just one more bare rock, the implications ripple outward across the whole galaxy. The most common type of potentially habitable real estate out there, rocky planets sitting in the habitable zones of small red stars, might turn out not to be genuinely habitable after all. That would mean life, if it exists anywhere else, likely requires a star more like our own sun, which in turn would mean such stars and such opportunities are considerably rarer than we'd hoped. We would, in other words, be more alone than we thought. But if TRAPPIST-1e turns out to have even a thin atmosphere, the story flips entirely. Suddenly, every dim, unassuming red dwarf scattered across the galaxy becomes a genuine candidate for hosting life. And given that red dwarfs make up somewhere around 70% of all the stars in the Milky Way, each one potentially surrounded by its own tightly packed cluster of rocky, telescope-friendly planets, the number of places life could plausibly exist would suddenly expand to something almost too large to fully comprehend. One planet, one answer, still missing. And somehow the entire question of whether humanity is alone in the universe currently hinges on what's hiding inside the noise surrounding one small, restless red star, 40 light years from the room you're sitting in right now. James Webb pointed itself at a planet that looks, on paper, remarkably like our own, and something about the result feels genuinely unsettling. Not because the planet itself is somehow wrong, but because the universe is making us work far harder than anyone expected just to hear what it might be trying to tell us. We built the most powerful telescope humanity has ever produced. We aimed it at our single best candidate for life beyond Earth. And it turns out the star that planet orbits is shouting so loudly that we still can't quite make out the whisper coming from the world beside it. The answer is in there somewhere. We just haven't figured out how to listen closely enough yet.